Third unit. That second unit and a big chunk of the first unit, we were talking about one variable quantitative data. So we had a whole set of numbers, and we analyzed how we could, or we talked about how we could show them visually using graphs, and we talked about how to analyze them by finding their measures of center, by finding their measures of spread or variability, by finding their location in terms of other data values, that's percentiles, by finding z-scores to compare two different sets of single variable data. Now what we're going to do, we're going to continue with quantitative, with numbers, except we're going to talk about two variables now. Okay? So two variables. And when we talk about one variable quantitative data, like we already have, we call that univariate data, uni being a prefix for one. When we talk about two variables and the relationship between the two, we refer to it as bivariate data. And the graph that we use to visualize those is something we call a scatter plot. And then we're going to analyze certain quantitative amounts, like we're going to analyze the relationship between the two variables, and it allows us to make conclusions. Okay. So the first thing, before we even start with the scatter plot and different numerical measures, is each of the two variables has a specific name. Okay. So using this example, HEB is a grocery store chain in Texas. So it's like a Safeway, it's like a Sobeys. All right. So this example explores whether there's a relationship between the neighborhood income in San Antonio, Texas, and the number of organic items that are available at the local HEB grocery store. So we've got two variables, income and access to organic items, or number of organic items offered. One of the variables we're going to call the explanatory. That's the independent. When we graph it, that's what goes on the horizontal axis. Okay? That's the variable that we're using to predict the other variable. So this is the x variable. And the one that's getting predicted, or the response variable, the dependent variable on a graph, the y or vertical axis, that's the measured outcome. Okay, so that's the y variable. So looking at this question here, the example, which variable would you think is the explanatory one? What's that?
Average household
income, average household income. Yes. Okay. So income, because we're using it to predict organic items offered. Which means that the other variable, the organic items offered, must be the response. Okay? So this is the organic items offered. because that's the measured outcome. So you can see we've got a whole list of data here that lists zip codes of the grocery stores, their specific location, the household income around them, and the organic vegetables offered at each grocery store. So we can see that, you know, we've got a location on South Flores where the area around this location, the average income is 71,000, a little bit over. They offer 36 organic items. And yet the next one, you can see this one is a lower income area, only 34,000, and they offer a lower number of organic items. So perhaps we can see a trend already. But obviously, it's really hard to see a trend by looking at a whole list of numbers. So we want to show this visually, and that's where Scatterplot comes in. So if we take all that data, and remember, income is the explanatory variable, so that's the X variable that goes on the horizontal axis. Organic items offered, that's the response variable, okay? That's the y-axis or the vertical axis. So we can see that here, this one's a little over 30,000, and yet there's only about, I think that's the second one we talked about, where the income was 34,000, the number of organic items offered was 4. And then we have up here with a high income area where the income is over 130,000, they're offering close to 100. And then we've got all the data in between. I'll explain this line in a second. Some of you may be familiar with it already from science courses. Okay? But just for now, look at the dots. Okay? And we want to see a pattern in the dots. And usually we see this pattern or the following patterns here. And when we talk about the relationship between the two variables, we talk about their correlation. Correlation means how, basically it's a number that tells us how strong the relationship is or how weak it is. So we can see here that if we have a series of dots forming a perfect line, that's a perfect correlation. Okay? That's very rare. This one looks pretty close to the one above. Okay? So it's strong and it's positive correlation. Okay? But it's not perfect. Once they start to get a little bit more spread out, but you can still see it generally forms a line. It's weaker. If everything's scattered all over the place, there's no correlation. Or there's no relationship. And then we get to the weak. Weak is when it goes down to the right. Or sorry, negative is when it goes down to the right. Positive is when it goes up to the right. So if it's going down and it's pretty scattered, that's a weak negative. If it's a little bit tighter, it's a strong negative. And if they're all form a perfect line, then it's a perfect negative. Okay? So we want to describe what does it mean for a correlation to be positive and what does it mean to be negative? Well, to be positive, what does that mean? It's a positive slope, yes. Okay, yeah. They're proportional. Try using the variables names.
Y increases,
As X increases, so does Y. Or as the average income increases, so does the number of organic items offered. Okay? In that specific example. So Yeah, that's right. As X increases. So does Y. And for negative, as X increases, what's Y doing? Decrease. So you can see we're describing it kind of different ways. Whether it's positive, whether it's strong, weak, or no correlation, how strong is it? Okay, and we'll talk about that in a second. Now, what we want to do, because we want to try and do this mathematically, okay, is we want to come up with a line that we can make an equation out of that allows us to make predictions. Okay? So we call this the least squares regression line. And I'm going to talk about why it's called least squares later on. But for the time being, basically, let's talk about it as a regression line or a line that sort of fits the data. Okay. So if we want to draw a least squares regression line for each of these, okay, well, in a perfect positive, I can easily draw a line that goes through all the points. That would be the regression line. And I could make very accurate predictions. So like if there's a number out here, I could get an equation for this line, plug the value of X in here, and I'd probably get the exact value of Y. Because it's perfect. Just like here, it would be a perfect negative. But what happens when it starts to get a little scattered? How do you think you'd draw it? Brooke?
I think a lot of the best fits where points kind of equal out so you make the points go.
Exactly. Yeah. We want to draw a line so that about half the points are above and half the points are below. So here, somewhere around there. For here, somewhere around there. That should be a little low. I'd do that a little high. I can't do that. Like that. If it's more scattered, well, you can still sort of see a line. Positive and negative. And for the middle one, well, there'd be no line. Okay. I mean, I guess you could draw a horizontal.
You draw the line that's you don't continue past that.
What's that? Normally, no. I mean, you can use it to make predictions, but the further you go away from the data, the less accurate those predictions are going to be because we don't know what happens, right? For all we know, if we see something like this, maybe all the dots start straightening out after as we increase X. Who knows? We can only tell within this domain. Okay. Okay, so just like we use SCIBO to describe a single variable quantitative distribution, we can use 4 factors to describe a bivariate situation. And those we can think of dots. So we want to talk about 4 things when we analyze a scatter plot, okay, and analyze the data with 2 variable data. First of all, is it positive or negative direction? Are there any outliers? And we're going to sort of eyeball outliers in this one. We're not going to calculate them like we did in the first unit with univariate data. Is it linear or non-linear? Does it form a line, the dots, or does it curve? Okay. Or is there no relationship? And how strong does it look? So I want to, and you can usually do this in 1 or 2 sentences. So I want to write a sentence that's somehow going to incorporate all these factors for this HEB data, the household income and the organic food items offered. So I could say the relationship between income, because we always want to write in context, between income and organic items offered. Why it keeps taking up pause. Is, well, is it positive or negative? Positive. Is positive. I'm going to save the outliers for a separate sentence. Form. Does it form a line?
Yes.
Yes. So we would say linear. And this is where it's a bit subjective. How strong would you consider this? I mean, it looks probably moderate would be a good description. And then, just like we did with univariate data, there appear to be no outliers. I mean, you know, look at the distance from each point to the line that's been drawn, right? I mean, this you may think of as an outlier, but it's really not that far from the line. If you think about it vertically, if you're thinking about it way out here, it doesn't make it I mean, it makes it an outlier in terms of income, but not an outlier in terms of the relationship. There appears to be no outliers. Statistics being a mathematical subject. We want to, yeah.
I'm just going to question the dollars.
Yeah.
Every volume is a Scatterplot next to the line. How many units dollars? And that's, yeah. Outlier.
Yeah, it's, I mean, you'll be able to see it. Like, I mean, you know, like here, you'll be able to see it. Like, let's say I add a point here. If I want an outlier, I'm going to add a point here. Like, that's an outlier.
And what the line also moves to.
The line.
Isn't the line also moves to down?
This way?
The line would be moved like the.
Oh, yeah. Oh, yeah. Sorry. It would, an outlier, you're asking a different question. Okay. Are you asking about how do we know what's an outlier or not? Or how does an outlier affect the line? Okay. So this would be considered an outlier. And you're right. It would affect the line. It would pull it down a little bit. But we're going to talk about that later on. We will. What kind of effect outliers have? Okay. So sort of the final thing here. The quantity called correlation, and it's denoted by a lowercase r. Okay. Measures, it is a numerical measure of the strength and direction. And And it will always be a number from -1 to +1, all numbers in between. Okay, it can never be lower than -1, because -1 is a perfect negative relationship like this. And it can never be bigger than 1 because 1 is a perfect positive relationship. Okay. And if there is no correlation, that means the correlation R would be very close to 0. And then you can see there's sort of degrees in between. So this one, pretty tight, pretty strong. So R is going to be close to 1, and it's going to be positive. Okay. On this side, it's a negative relationship, and it's pretty strong. So it's so it's going to be close to -1. Yeah. You can. Yes, there is a formula to do it. You can do it on your graphing calculator. So we will talk about it, how we can get the correlation. Okay. Yeah, I mean, it's possible. It's very long to do it by hand. So we use a graphing calculator. And if it's weaker, positive, you can see that it gets closer to 0 than it does to 1. Okay. And this one here is a weaker negative. So if R is close to 0, we would say that there is a weak correlation. If R is close to -1 or +1, we would say that there's a strong correlation. If R is negative, it's a negative correlation. If R is positive, it's a positive correlation. And just to sort of give you a ballpark, okay, in general, if R is 0.8 to 1, or -0.8 to -1, we would consider that strong. So if you're looking at 0.8, 0.9, or any number in between there, or any number between 0.9 and 1, that's strong. Same within the negatives. If you're looking at this, you're looking at models. And I mean, you could even say moderately strong or moderately weak. So one could argue that the ones here that are 0.48, you could say moderate, but you probably want to put the word weak with that. And if you're from 0 to 0.5 in a positive relationship, or 0 to -0.5, now we're talking weak. Okay. I want to see if I have this. Sorry, I'm just changing here. Yeah. There we go. Okay, so here. Give me a number. That represents this correlation. What do you think your guess would be? So -0.5. Does anybody want a different guess? Do we agree negative? Yes. So now we got to think about the strength. You want 5.5? Let's see. -0.671. Not bad, not bad. That one. We're gonna go negative again. Try 3. Negative 0.453. Zero 0.8, 0.7. Okay, let's go 0.75. 0.673. Ooh. Oof. I mean, does it, how do you even tell if it looks positive or negative? So we want to go, okay, well. 0.163, so they're saying it's slightly positive. Anyway, that gives you sort of an idea of what those numbers look like. Okay. I do want to talk about, I'm not going to write anything down, but here's an interesting example. From 1994 to 2020, the statistician collected 3 pieces of data. The average temperature, okay, during the summer days, the amount of ice cream sold at the beach shop, and the number of drownings. Not pleasant. And he looked at 2, or she looked at 2 relationships: the average temperature and the number of ice cream sales. We would expect that to probably be a fairly strong positive relationship. If the temperature is warm, a lot of people are going to be at the beach, which means a lot of people are going to be buying ice cream. But he also, or she also, looked at this. As the average temperature increased, so did the number of drownings. So I think we can look at, now technically, if we look at both of these, how would we describe them? Remember, DOFs, the 4 factors: direction, positive, strong, linear. Doesn't seem to be any outliers for each one. So they look exactly the same. However, the second question is probably more important. Do both of them make sense? I mean, the first one, I think we could probably agree, yeah, it makes sense. Okay. But does the second one make sense? You think so? The warmer the temperature, the more likely people are going to drown? Okay. Could there be something other that increases the number of drownings? Could be some other variable? What? The what? The what? So the more people there are, the more people that are unlikely to swim, therefore increasing the number of drownings. Possibly. I would say, in general, the second one's a little iffy. You can make an argument, and you guys did, but chances are there may be some other factor involved. Okay, so I guess if we did the number of the amount of ice cream sold and the number of drownings, we get the same thing too. Yes, I mean, like, this is what I mean by statistics is an art as well as it is mathematical. Because you have to sort of look at the 2 variables. Because you could make an argument for anything. Like, the number of AP stats students has increased over the years. So has the number of deaths because of getting caught in blankets and suffocating. Believe me, that's an example. It's an example of what I do. So if you take AP stats, does that mean your risk of dying in your bed increases? Because you're so stressed about the test and you're twisting around and you twist yourself into a mummy and you can't breathe. Ay, ay, ay. Ay, ay. Okay.